In this video I'm going to talk about the intermediate value theorem. So let's say that so if f is continuous on the interval from a to b, then for any v between f of a and f of b, there exists point C such that f of c is equal to v. So basically what it means is that, like, if we have a function, like, to illustrate this, so let's say here is a and here is b. So it means that all values between f of a, so this is f of a and this is f of b, so all values between these two values, they're attained by the function somewhere in the interval. So for any value v that we choose, there exists point C. In this case there are 3 points, but we need to prove that there is at least one point C such that this value is a value of the function for some point C. So let's prove it. So first, without loss of generality, we can assume that f of a is less than f of b. Well, strictly speaking, like, without loss of generality, we can assume that it's less or equal, but the case when it's equal is trivial. So when f of a is equal f of b, then the only value that we need to prove is the value f of a and f of b itself, and of course it's achieved in both a and b. So the case when f of a is equal to f of b is trivial, and we assume that f of a is less than f of b. When it's greater than f of b, this case is considered symmetrical. Okay, so now we are going to take our interval, so interval from a to b, and we are going to divide it into two. So we consider the point, so let's denote a as also a1 and b as also b1, and this point, the middle of this interval, we would denote as c1. So which is like a1 plus b1 over 2, exactly the middle of the interval. So there are two possibilities. So either f of c1, like, it could be either it could be either less than v, or it could be greater than v. Well, it also could be equal to v, but if it's equal to v, then we have nothing else to prove. So if f of c1 is equal to v, so then we are done with the theorem. So we only need to consider these two cases. So when it's less than v and when it's greater than v. So in this case, we take basically the idea is to take a sequence of intervals. So when f of c1 is less than v, so v, so remember that because of this inequality, so v is between f of a and f of b, right? So we need this also to hold for a1 and b1. So we need this similar inequality to hold for all indices. So we construct the interval we take the interval from C1 to B1 and denote it as the interval of A2, B2. So basically we set A2 to be C1 and B2 to be B1. And in this case, we take the interval from A1 to C1 and denote it as A2, B2. So we define basically the interval A2, B2 as one of these two intervals. So like C1 divides the whole interval from A1 to B1 into two intervals, from A1 to C1 and from C1 to B1, two halves. And we take one of them as the next interval in the sequence, and we choose based on we choose one of them such that this inequality would hold for the next index. So with this choice, we guarantee that. Okay, so let's remove this. We guarantee that V is between f of A2 and f of B2. Right, because in this case V is greater than C1, and C1 we set to A2. So this inequality is exactly this in this case. And the second inequality, because B1 is equal to B2, so the second inequality holds from the previous step. So from this, V is less than f of B1. And similarly, in the second case, when f of C1 is greater than V, then C1 is set to B2. So then this inequality is exactly this. And the first inequality is, because A1 is equal to A2, is exactly this. Right? So yeah, so we choose the interval such that this inequality holds. And we continue this process again. So again, when we have the interval from an to bn, we divide it into two. This is cn equal to an plus bn over 2. And we choose one of these intervals as the next interval, depending on which of these two possibility holds. So now we simply replace the indices here. So we say that either f of cn is greater than v or less than v, and depending on that we choose the interval a n plus 1, b n plus 1, n plus 1, bn plus 1 to be either cn bn or an cn. So they're very similar analysis, and we get that this inequality also holds for n plus 1. So basically with this construction we get a sequence of intervals. So we get a sequence of intervals a1, b1, a2, b2, and so on, an, bn, so on to infinity. And we know that we notice that they are not just intervals, but they're like the next one is strictly is inside the previous one. So we can, instead of writing commas here, we can write the other way around. The next one is contained in the previous one, right? And we also notice that the length of the intervals is so the length of b n plus 1 minus a n plus 1 is equal to 1/2 of the length of the previous interval. So therefore, like the length of the nth interval bn minus an, when we expand this chain of quantities, it will be 1 over 2 to the power of n of the original interval b1 minus a1, or b minus a, which is the same thing. And so this, we notice that this tends to 0 when n tends to infinity. So the length of the interval of the intervals tends to 0. And so because of that, so basically and for every interval also we have that do we have it here? Yeah, like basically this equality, only here it's written for n plus 1, but we need it to hold for every n. So we write that for every n by construction. V is between f of an and f of bn. Yeah, so now we consider the sequences an and bn. we notice that an is so we notice that both of them are monotone. So it's so A1 is less or equal than A2 is less or equal than A3 and so on, less or equal than AN and so on. This is simply from like this is another way of writing this chain of inclusion of the intervals. So the same for Bn. So P1 is greater or equal than P2, greater or equal than P3, greater or equal than Pn, greater or equal than, and so on. And so, so the sequence B1, so the sequence An is monotone, it's increasing, and it's bounded from above by B. So An is increasing, not strictly increasing, but just increasing. Increasing, and it is bounded from above. So An is less or equal than B. Therefore, we conclude that it converges. There is a theorem that says that if a sequence is monotone, if it's increasing and it's bounded from above, then it converges. Converges similarly for Bn. So Bn is decreasing and it is bounded from below, so it's greater or equal than A. Therefore, we conclude that Bn converges. So the sequence of An and Bn, they are convergent, and because the length of the intervals tends to 0, because of this, these two sequences must converge to the same limit, because the difference between them converges to 0. So because En minus An converges to 0 when n tends to infinity. Therefore, the limit of An when n tends to infinity is equal to the limit of Bn when n tends to infinity, and let's denote it by some number, or not n, but let's denote it by the number yeah, actually we don't need this limit. Yeah, it's true that they converge to the same limit, but we actually don't need it. So what we need is we need the sequence Cn, which is the Cn is equal to an plus bn over 2. So the sequence of the middles, the midpoints of the intervals. No. Okay, so let's denote this limit by c, and so let's denote this limit by c. So we know that c, of course, is in the interval from a to b, because all an and bn are in the interval. And we know that so because we had the inequality that v is between an and f of an and f of bn for every n, so we know that the sequence um, yeah, so we know that the sequence f of an converges to f of c. This is because of the continuity of the function. So the because of the continuity basically means that the limit that the limit of f of an can be written as f of limit of an. That's the that's what continuity of the function means, and this is this limit is equal to c. Right, so this is equal to f of c. And similarly, here, so f of bn converges to f of c because of the continuity of the function. So now we have the sequence f of an that is less than v, f of n that is less than v for every term of the sequence, and it converges to a certain limit. Therefore, the limit must be less or equal. So because of this inequality, okay, let's remove this. So this inequality implies that the limit f of c is less or equal than v. And the second inequality implies that, like for every term, implies that the limit f of c is greater or equal than v. So basically, when we take the limit of this, inequality, the strict inequalities are converted into less or equal. So f of c is less or equal than v, less or equal than f of c. And because of this, we conclude that, because on the left and on the right is the same thing, we conclude that f of c is exactly equal to v. Yeah. And this concludes the proof, because we found the point C that satisfies what we need to prove.